Okay, hi. Yeah, I'm Ben. So I'm going to talk to you about some interesting work that we're doing on the spinal cord. So this is a treatment that probably not many people are familiar with in here. I hope you're not familiar with it, because if you are, then you have drug refractory chronic back pain. But it's a treatment modality where we put a small electrode actually implanted into the spinal cord. It sits on the spinal cord tissue, actually in between or within the spinal column. So it's a very popular treatment in the US, less so in the UK, but it's becoming more popular. Usually these are patients who have had opioids thrown at them for years. They are like the worst of the worst of back pain or sciatica or angina. It's not working anymore, so we use this. Basically, the devices, they deliver a very small electrical pulse to the spinal cord, and that kind of disrupts the pain signals that are going on in the spinal cord. It's connected to a small battery and the computation as well that sits kind of implanted down by the sort of kidney in the back. So these treatments have been around for 50, 60 years now. They're not particularly new, and basically the front end technology, the actual electrode part, they kind of haven't changed in that time. They're relatively bulky, they're made of silicones but kind of vaguely inflexible. They're made of like hard platinum, and this causes like irritation to the spinal cord as well. But they work. There are two types of these devices, broadly. We have these paddle type devices. So these are 2D arrays of electrodes, which, as you can imagine, it means you can address the electrical field a bit better. So it means that you can like tune the stimulation to some point on the spinal cord. And they actually stay in place. Just mechanically, they stay in place quite well. Then we have these percutaneous lead type devices. They're much, much smaller. They're about 1 millimeter in diameter. But they can be implanted super, super easily because of this, because they're 1 millimeter in diameter. That's why I've got this guy. So if you've got a paddle type device, you have a laminectomy. It means you actually remove part of the lamina. A surgeon comes in, they chop part of that bone out, they chuck it somewhere, I don't know, it's incinerated, I guess. It doesn't go back in you, you're left with this kind of for the rest of your life. The percutaneous leads, on the other hand, they slide in between the vertebra, navigate up the spinal cord. Surgery is way less complicated, way less risky, and it means that if you're overweight or diabetic or you're immunocompromised in some way, you can still have these surgeries. So kind of triggered like an interesting question in our lab, and I'll go into what our lab do in a minute. But can you combine these two technologies? Can you make a kind of paddle type electrode that you can unfurl onto the spinal cord, but use very, very minimally invasive surgeries? As I say, this is a treatment that's been banded around for the last few decades, half a century, but it's getting quite exciting now. We're starting to explore spinal cord, both stimulation and recording for rehabilitation following spinal cord injury. So if people are paraplegic or quadriplegic, you can start to treat them with these stimulating technologies, and also gait disorders in Parkinson's patients as well. So what do our lab do? Our lab build very, very thin, flexible electronics using manufacturing methods that are kind of inspired by the semiconductor industry to make devices that are really, 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 really thin. So human hair is maybe 50 microns in the order of. Our devices, we go down to about 4 microns. It means they're really conformable. It means that if you sit them on the brain or the spinal cord, they follow the curvature, they sit nicely, they stay in place. The devices that are out there at the moment were 2 millimeters. They're not flexible at all. So we wanted to make a device that we could package up inside a needle, thread up into the spinal cord, and then using fluidic or pneumatic actuation, actually unfurl it onto the spinal cord and do broad area coverage on the spinal cord. Our lab is all about translation. I work with a bunch of neurosurgeons, and we're trying to get these into humans. We're not interested in just publishing a paper and forgetting about it, that was kind of cool, fun engineering project, but we're done now. We're talking about actually translating these into patients, and such. We have very key design criteria. That is that it has to be fabricated from biocompatible materials. We can't use crazy materials that are never going to get into a human. We have to introduce them using standard percutaneous techniques, the sort of techniques that surgeons already use. We only want, this is very important, we only want lateral expansion. We don't want this device to balloon in the spinal cord, because if you implant something, you pump it up like a balloon, it puts pressure on the spinal cord, you're going to cause more injury than you're going to have benefit. So we need this device to just unfurl laterally. And we need it to be suitably packaged inside a geometry that makes sense for us. It's kind of the boring engineering side of this, but it's incredibly important that we have 16 electrodes on this. Every single one of them needs to be connected to a wire that goes south down to a battery with some fluidic connections. All of these things need to fit inside that needle, which is actually a surprisingly difficult engineering challenge. So this is what the device looks like. This was our kind of first iteration of the device. This is it being tested in an in vitro model. So we set up something that kind of simulates the environment of the spinal cord. That is like a balloon inside a tube, just restricting space. And then we actuate this device to unroll those electrodes onto the spinal cord. This is the device on the right-hand side. The kind of front end that you can see with the electrodes on it. This pointer doesn't work either. With the electrodes on, that's the part that would actually sit on the spinal cord. All the wires then run down to a battery further down. The device is maybe 50 millimeters, the front end, the sensor that actually sits on the spinal cord, and then the rest of it's maybe 500 millimeters that runs down to the kidney. So we developed this nice device. We say, now let's go into a human. We do a human cadaver model. We set the human cadaver model up. We implant the device, and there it is. You cannot see it. So it turns out they use X-rays to actually navigate these devices. And when we make these devices so thin, we make them down to 100 nanometers in thickness, the actual metal layers, you can't see that on an X-ray anymore, which was a huge problem. And when I talk about translation, it's so important for us to actually, a surgeon would turn to us and go, well, what, I can't use this. I can't see where the hell it is. So we actually spent quite a lot of time, in the interest of time, I'm not going to go through all of this development, but we actually spent quite a lot of time then developing X-ray compatible markers that we can implant on the device so a surgeon can actually navigate the device. So this is what a kind of surgeon would be used to seeing. Our device obviously you see nothing, but then we develop these markers, and then the device looks more like this. So this kind of block dark area here is a steel needle. And then coming from the mouth of that needle in the red box, you can see our device there like emerging. The surgeon is navigating that up the spinal cord, and then we actuate the device, and you can see those two lines widening. That's the perimeter edges of our device spreading over the spinal cord. And we do some basic electrical testing then just to make sure the device is open and on the spinal cord and functioning how we would like it to function. So my talk was called The Dark Side of the Spinal Cord. This is a reference to one of my favorite albums, not a reference to Star Wars. But what do I mean by the dark side of the spinal cord? Well, all of these devices that are out there at the moment, or these clinically available devices, but also the research devices, they look at what we call the dorsal part of the spinal cord. So simply this area here. It's an interesting area for pain management because that's where all your pain fibers are, or the majority of your pain fibers are. But the spinal cord has a pretty complicated architecture. We have this white matter around the outside that can be thought of as kind of cables running up and down. So motor information coming from your brain, down your spinal cord, in these red sections, down to the periphery. And then pain in the periphery being sent back up these, or pain or touch or temperature being sent up these blue pathways up to the brain. Looking at the dorsal part of the spinal cord is super interesting for pain, but if we're looking at motor information, spinal cord injury or Parkinson's and movement disorders, we really want to explore the entire circumferential area of the spinal cord. This has been done in research using something called interspinal microstimulation, but it's you're basically sticking metal shanks into the spinal cord. Now, the spinal cord is very, very soft, very, very squishy, and if you stick metal probes into it and the person moves, as you hope they will and would, it destroys the tissue. So using our kind of technologies, we have these very thin, very soft interfaces, and we want to wrap these interfaces around the spinal cord, and then we start to explore utility. Okay, so we can, using these kind of like actuated soft devices, we can wrap all the way around the area. What can we do there? Can we explore the motor information on the kind of, what we call the ventral side of the spinal cord? This is the front of the spinal cord. I should also mention why we're usually only accessing the dorsal part. The dorsal part is the back. Very easy for a surgeon to access. If you start probing around the front with kind of rigid or semi-rigid technologies, you can very, very easily damage those pathways, and it's something that we absolutely don't want to do. So this is the next device we've developed. We call it the i360. It's a device that can actually, as I say, navigate and wrap all the way around the spinal cord using a relatively simple surgical procedure. 1 minute remaining, excellent. And we can start to generate like very cool visuals. So this is what we call electrophysiology. We're measuring the electrical signals from around the spinal cord. And what you can see in the red here is what we've done on a rodent model is we've stimulated the periphery. This is an anesthetized animal, so they're feeling nothing. But we stimulate the periphery in the lower limb, the leg. And what we're seeing is a pain signal on the dorsal part of the spinal cord. Then, milliseconds later, we see a flash on the ventral side of the spinal cord. Now, what we're sort of postulating, what we theorize is, what we're seeing there is a reflexive pathway. We're getting a signal coming up the spinal cord. We get some interneuron activity, and then we get a signal on the ventral part of the spinal cord. This opens doors to neuroscience that we don't do currently. We don't explore and probe 360 degrees of the spinal cord, and we're working with collaborators now to offer this as a kind of research tool. So I'm running out of time, so I'm not going to talk any more about that, but I'd love to if anyone wants to speak to me in the break. We can keep talking. I've probably got about 60 minutes of material here, so I'll stop. But I just want to offer some conclusions. Shape-changing and thin film and soft electronics, they offer us a new paradigm for minimally invasive implantable medical devices, and we want to start exploring this in other parts of the body, so the brain, the peripheral nervous system. Also, broad area spinal cord interfaces offer us new tools for neuroscientific research, but also, you can imagine these devices being used for neuroprosthetic applications. So we can put a ring of electrodes around the spinal cord, record from that, and then we can do what's called functional electrical stimulation, that is like stimulation of the lower limbs, or neuroprosthetics, bionics. Of course, I'm not working, no man is an island, I'm not working on this project on my own. I have an incredible team around me. George Maniaras is my PI. He's a phenomenal technologist and a great guy. Damiano is the neurosurgeon that led the clinical work on this. And a massive shout out to this guy as well, Jiang Li, our Singaporean collaborator, who did an absolute phenomenal effort on the recording side of this work. Yeah, thank you so much, and please, questions, I welcome them.
Thank you, Ben. It's a very interesting topic. Is there any question from the audience? Yes.
Thank you. Very interesting talk. It seems to me that you, in principle, have a radio frequency coil, or you could make a radio frequency coil out of your implant. I was wondering whether it could be combined with magnetic resonance imaging to get direct information from the spinal area.
Absolutely, for sure, you could. Actually, the interesting thing about these devices is because they are thin, because we use thin layers of metals, they then become compatible with MRI imaging. So the traditional devices with a few hundred microns of metals, they're incompatible with MRI for reasons that you get artifacts and also heating. But yeah, with these we've done these tests where we can couple them with MRI. We haven't explored that as like a research area, but for sure.
Thank you.
Is there any other question? Here first and then there.
I just wonder what's the likelihood that these would be implemented? I mean, are there huge restricting factors such as cost? Is there a big difference to the technology that's currently being used and the technology that you've developed?
Mm-hmm. The cost of these devices, the traditional spinal cord stimulators, they're about 20 grand. They're expensive. They're really expensive. A lot of that cost comes down to regulating medical devices is incredibly expensive. We would be no different. We're trying to build, validate, and regulate a class 3 implantable medical device, which is just a difficult thing to do. The difference actually where we might save a little bit of cost is these devices that are out on the market at the moment, the platinum-based devices, it's a very manual process. You have to hand build them. You have to basically do something called resistant welding on all the wires and everything. I've seen people building these, and it's time-consuming. I asked someone, how long does it take to build one of these devices? 5 days to build one of these devices. There are people there with like tweezers taking pieces of platinum out. Whereas because we're developing these devices based on these approaches from the semiconductor industry, we make all of them on a wafer. We do something called lithography, so we just batch manufacture things. There is, of course, there's still manual aspects of connecting things up at the end, but the process is a lot quicker, and we can scale things a lot easier. So we could probably bring the cost down a little bit in terms of actual manufacturing, but of course the cost comes for the regulation. So
to cancel the noise, to cancel the pain, you need to measure the signal first. And then you have to, in noise cancellation, for example, measuring the characteristics of the signal is quite important. And then you need to cancel, in the time, it's quite important the way to do it. Are you able to measure the characteristics of that signal of the pain and also to apply in a certain time to cancel it out?
Mm-hmm. So there's two parts to this question. The devices that are out there at the moment, we wouldn't measure the signal to cancel it. So it works on a function where the kind of fast conducting pain fibers are silenced by stimulating, the slower conducting pain fibers are silenced by stimulating the faster conducting mechanical or touch fibers. So like the way that my neurosurgeon collaborator always describes this is like if you whack your hand on something or you burn your hand on something, like the first thing you do is you rub it, and it's like your body basically like smothering those signals with like something that's more tolerable to you. And we do exactly the same. So we stimulate with like a low frequency signal that feels like tingling, and that actually just hides, masks the pain. But the other part of your question is, actually recording these signals, and can we like differentiate between them? That is very important for the rehabilitation and the motor side of things. So what we actually did in these experiments, which we're going to publish quite soon, is we stimulated different nerve fibers. We looked at like sciatic nerve versus tibial nerve and looked at the shape, the waveform of those signals. And yes, we can kind of stratify them and classify them based on where they're coming from. We haven't done this yet, but I imagine we'd also be able to then stratify based on like whether it's like a C fiber, A fiber, blah, blah, blah. Like we'd look at like temperature versus acute pain, probably where we'd go, but with our collaborators at this point.
I'm sorry. Thank you, Ben, and thank you for the questions. So our second speaker is Lucas de Lima Camillo. He will be presented his work entitled Unraveling Aging with Deep Learning.
Okay. So I just realized that I forgot to put a cover slide, but my name's Lucas, and I'm going to be talking about aging. So don't quote me on this, but I think that was a former UK Health Secretary who said something along the lines of, the NHS currently stands for National Hospital Service instead of what it actually means, National Health Service. And I think this quote is very telling in the sense of how medicine works nowadays. So we're pretty good at avoiding people from dying, but when it comes to avoiding people developing disease in the first place, we're still not that good at it, with the exception of vaccinations. So an analogy that I like to make is that healthcare is similar to a game of whack-a-mole. So imagine someone who's 50, goes to the hospital, let's say with diabetes. The main mission of the physician and of the hospital is to make sure that the person doesn't die there. So hopefully that 50-year-old is going to be treated for diabetes, but inevitably a few years later, that person is going to come back to the hospital, let's say with cancer this time, and then again, the main mission is to make sure the person doesn't die. Then a few years later, going back to the hospital with some other type of condition. So I think this plot sort of portrays this phenomenon really well. So on the y-axis, you can see your chance or probability of dying in a given year. And on the x-axis, that's your age. I think this is US data. And it's a bit of a frightening curve because you can see this very exponential increase, especially after the age of 50. And this is just for the risk of dying. So if you look at this curve, but instead of for dying, for other age-related diseases, so diabetes, cardiovascular disease, dementia, etc. It's similar in that it's exponential in nature, but it's even worse because it's literally shifted to the left. So the age of onset of things start much earlier. So can we do something about it? And I would say that the answer is yes, and I'd argue that the best way to do it is targeting aging itself. So in order to make sure that a pro-longevity treatment actually works, you have to do a clinical trial. So during the first phase, it's preclinical, so doing research should take a few years to test in mice in the lab. Then after that, there is phase 1, which you test for safety in a small cohort of humans, and that should take a few years or so. But the main roadblock happens in phase 2 when you're testing for efficacy. So to make sure that a pro-longevity treatment works, ideally, you would follow people throughout their lifetimes to make sure that the risk of developing all of these age-related diseases actually goes down. And phase 3, it's similar, it's just a much larger cohort. Sorry about that.
Oh, it's back. Okay.
Okay, phase 3 and then phase 4. And after 150 years later, you finally launch your product. And I'm pretty sure this is a little bit longer than most of us would be willing to wait. But there is a solution. And the solution is to create a clock, but not one that measures chronological time, but one that measures biological time. So what do we mean by this? You can imagine two people of the same chronological age, but one smokes, is sedentary, and doesn't exercise, and the other one does the exact opposite. So you can imagine that one of them is aging at a much faster rate than the other one. So this concept of biological age can sort of help speed up the timeline of a pro-longevity clinical trial. So for phases 2 and 3, instead of literally tracking people throughout their entire lifetimes, you can do something very simple. So using this biological clock, you can measure everyone's biological age at the very beginning of the study. Then after a few years of treatment, you measure their biological age again and see if there was any difference. So you can probably cut down that time to about 5 years. So in total, 20 years, that's a much more reasonable time scale. So there are a few different biological clocks. I would say that the most noteworthy of them was one developed a few years ago by a professor at Berkeley. And he uses a type of DNA modification called DNA methylation. So there's little balls that get attached to DNA. They change over time and with lifestyle and a bunch of other things. And his clock works for most tissue types. And it has a prediction error of about 3.5 years, which is kind of amazing, to be honest. And it's also very easy to interpret. But when he was creating his clock, he used a linear model. So he made two main assumptions. So one is that all the variables are linearly related to age, and the other one is that there are no interactions between variables. So what I've been working on for the last 1.5 years was on how to improve this multi-tissue biological clock. So if you Google my name and clock after, this should probably show up. It was published 10 days ago, so it was pretty recent. And the name of the clock, it's called Autumn Age. So it uses the same type of DNA methylation data as the Harvard clock. You have the first step of pre-processing, and then the second step, it's when you actually input the data into Autumn Age, which is a deep neural network. Some dark magic happens in there, and then you have the predicted age as the output. So this is just a quick comparison between the two. So Autumn Age seems to work for all tissue types instead of just most of them. The prediction error is a little bit over 2 years instead of 3.5. And there are also no assumptions of linearity and no interactions between the variables. And the other advantage is that you can get much deeper biological insights from looking into the model. So just 2 examples of the types of insights that you can get is that you can look at one specific DNA methylation site in the genome and see how that impacts the predicted age. So it might be a straight line going up, a straight line going down, a curve, or another type of relationship. And the other type of insight that you can get from Autumn Age is that you can look at how one specific DNA methylation site in the genome influences the importance of other DNA methylation sites. So from that, you can sort of get a better understanding on the gene regulatory networks that underlies the biology of aging itself. And from this, you can make some data-driven hypotheses about what's going on during aging. So these are just a few curiosities, I would say. So cancer seems to be older than normal tissue by 4.5 years on average. So if you mess up with cells in many different ways, so you can destroy their mitochondria, you can mess up with their immune function, they seem to get older. And patients with many different types of conditions, so type 2 diabetes, fatty liver disease, multiple sclerosis, they also seem to age faster. And just a few acknowledgements. These are the 2 professors that helped me do this project. They are a bit far away, so they were not able to come here, for obvious reasons. But this is it. Thank you.
Thank you very much, Lucas. Is there any question from the audience?
Thank you. I have, well, two smaller questions. The first one is, how do you validate the age? So you're saying there's 2 years closer to the real age or the real biological age, but how do you confirm what the real biological age is? And secondly, are there different ages in different tissues, and how can you sort of bring that together? Like your liver is maybe more old than your brain, for example.
So for the first question, I would say that since the model is regressed on chronological age, the assumption is that that difference from the chronological age and the predicted age, that should sort of tell you about biological conditions, and in the end, that's what's happening. A true biological age, which is completely independent of chronological age, then that's a bit difficult to imagine because you have to come up with different parameters. So one way you can sort of do that is calculate age as a percentage of lifespan. So instead of saying, oh, you're 50 years old, you can say, oh, you've lived 50% of your life. So you've used 50% of your time. So this is one way to sort of tell your biological age. And for your second question, there seems to be evidence that different tissues in your body age at different rates. So you can use, this is a multi-tissue clock, so you can get a sample from anywhere. And they usually are not exactly the same value. There's a general trend, of course, but some tissues seem to age a little bit faster than the other ones. So the brain seems to age a little bit slower, and that's a notable exception. But yeah, you can have these different ages in a single body.
Probably a stupid question, but so some cells in the body tend to regenerate and we have new cells from time to time. Does it make the age lower?
Could you speak a little bit louder?
Oh, yeah, sorry. There is some cells in the body that are new every day. So does this make the tissue look younger with your model or not?
You mean if there's an intervention that can make the clock get younger?
No more. You tend to change your cells from time to time. That makes sense? Okay.
Well, so you can, well, for neurons, which are post-mitotic tissues, so they don't really expand, they also age. And if you look at skin, which is a highly proliferative tissue, that also ages, and you can have a very accurate measurement of the tissue. So even though some cells are not dividing, some muscle cells, for instance, they also age, and the clock also captures that.
Thank you so much for this fascinating talk. So you started by talking about the issue of generating evidence of anti-longevity treatments or measurement. Why wouldn't a retrospective study be acceptable in this situation?
So this would be a prospective study. Of course, retrospective study, you can sort of look in the past and see if some drugs that are already approved have some evidence that they sort of reduce the age, the risk of age-related diseases. And there are a few drugs out there with some retrospective studies. One of them is metformin. Another one, it's a SGLT2 inhibitor, so it's another diabetes drug. So you do have valuable information from retrospective studies, but the golden way of sort of making sure that a drug works would be a prospective randomized clinical trial in the future. So of course you can gather evidence from what's out there, but if you're trying to develop a completely new intervention, then you wouldn't be able to look in the past.
Okay, thank you for the question. Thank you, Lucas. So now our third presenter is Sophie Sanford. She will be talking about her work, Antiviral Immunity in Models of Alzheimer's Disease Pathology.
Thank you. So, what is the role of the immune system in Alzheimer's disease? And this is the question I'm trying to answer in my PhD. My name is Sophie, and I'm based at the McEwan Lab in the UK Dementia Research Institute. So we know that when a virus infects our cells, the virus replicates, and that process is recognized as foreign. That virus shouldn't be there. And your cells have a response. Your cells produce really important immune molecules, and one of which is called type 1 interferon. So it's called interferon because it was discovered to interfere with viral infection. And it does this by causing a pro-inflammatory response. So all these immune cells rush into the area of infection to clear the virus. It also acts as a warning molecule, so neighboring cells are alerted of an oncoming viral infection. What's really interesting for us is that in Alzheimer's disease, as well as with age, and in things like traumatic brain injury, the level of this antiviral warning molecule interferon is really upregulated. So it's really a lot higher than normal controls, healthy controls. And so what I'm trying to answer is, what is this high level of interferon doing to influence Alzheimer's disease pathology and the development of Alzheimer's disease? So we know that in Alzheimer's disease, the brain shrinks. You get atrophy because the neurons are dying. And one other thing we know is that when you look at the post-mortem brain of an Alzheimer's disease patient, you see these aggregates, these clumping togethers of proteins. And one of the proteins in your brain that aggregates is called tau protein. And it forms these neurofibrillary tangles. That's just how we call this clumping together of that tau protein inside neurons. So what is this protein called tau? And I want you to close your eyes and just imagine you're inside a brain cell, and there's a train running from one end to the other. And that train is transporting cargo, is transporting nutrients, keeping the brain cell healthy. And what tau protein is doing is it's stabilizing those train tracks. In Alzheimer's disease, that tau protein comes off of the train tracks, so that train can no longer run, and your brain cell becomes unhealthy because it doesn't have the nutrients it needs, causing neuronal death. This seems really consistent with this graph here, where the more of those aggregated, clumped together tau proteins that you have, the more cognitive decline that you have, the worse the cognitive score. So what we're trying to do is figure out ways we can reduce the number of these tau neurofibrillary tangles, these aggregated tau species, to understand how we can reduce cognitive decline. And so we need ways of modeling the development of these tau aggregates, of these tau clumping. And that's what I do in my day-to-day. So I work with a model of tau aggregation in a dish, in some cells in a dish. And all that means is that I culture some brain cells, some neurons, and some immune cells in a dish. And the tau doesn't aggregate on its own. It doesn't clump together on its own. So I need to induce it using this thing called a tau seed. It's our way of sprouting this tau aggregation. And I can stain for the aggregation. Here, you can see a really big difference in the aggregation of tau. And it's our way of modeling what's happening inside the human brain here to form those neurofibrillary tangles. So I wanted to know, what is that really high level of interferon doing to influence this process of tau aggregation? And so that's what I did. I treated these cells with interferon. And what I saw was really interesting. So this is the control condition. There's no tau aggregation. This is the seed condition where I've induced the tau aggregation. And then when I added the interferon, there was a significant increase in tau aggregation. And this is what we believe to be the first time this has been shown in this model system. So I've just quantified that image in this graph here. So this is the tau aggregation percentage, and when I add the interferon, there's that significant increase in tau aggregation. And I was lucky enough to repeat this experiment in cells that don't have the interferon receptor. So all that means is that those cells can't respond to interferon anymore. It's as though it's not there. That's because they're missing the receptor that's on the surface of the cell to bind to that interferon warning molecule. And when I repeated that experiment in these cells, interferon no longer had an effect, which seems to suggest that it's really down to this interferon response, this antiviral response, that tau aggregation is increasing. So what happens if I block that response? Can I reverse the effects of interferon? And this is that interferon receptor I was talking about. On the surface of the cell, it allows that pro-inflammatory response to happen after the interferon is produced, that warning antiviral response. And what's lucky for me is that a drug already exists that it blocks this interferon response. It's called baricitinib. It's already being used for rheumatoid arthritis at the moment. So it's an approved clinical drug. And so I wanted to know, does this drug reverse the effects of interferon? So again, I'm just showing you a graph looking at the amount of tau aggregation in these cells. So going from left to right, as I add the interferon, there's a significant increase in tau aggregation. And what was really cool is that when you add this drug, baricitinib, you can bring the level of tau aggregation back down to the level without interferon. So you can indeed reverse this process, this interferon effect, using a drug. And what's really exciting for us is that this drug is already in clinical trials for Alzheimer's disease. And so I'm really looking forward to seeing what happens in this clinical trial. So the story so far is that the type 1 interferon, this antiviral warning molecule, increases tau aggregation in this model that I've shown you here. But this is a very short model. It's only 2 weeks that it takes me to look at this and get the data. Does this finding hold true in a whole body system where it's not just cells in a dish? And so this is what I've been looking at as well. So I've been looking at a long-term in vivo model of tau aggregation. All that means is that I'm looking at mice which develop those neurofibrillary tangles, those tau aggregates. And I've been comparing a group of mice, just a normal, that are normal, with mice that can't respond to that interferon anymore. So that interferon response isn't going on in those mice. And comparing how their tau pathology is. As expected, the lack of the interferon receptor, so when they can't respond to interferon, that means they have less inflamed brains. But do they also have less tau aggregation? Do they have less of those neurofibrillary tangles? Well, I was looking at the staining, and I was staining for those neurofibrillary tangles, again, the same ones that you saw in the human brain image that I showed you earlier. And when the mice can't respond to interferon, the level of tau aggregation, the level of those neurofibrillary tangles was significantly reduced. So this seems consistent with type 1 this interferon antiviral molecule increasing tau aggregation, both in a cellular system, in vitro, in a dish, but also in vivo, in mice, in a whole body system. So to summarize, we've shown that the antiviral interferons increase the tau aggregation. And the potential model that we have is that things like Alzheimer's disease pathology, so those protein aggregates, the neurofibrillary tangles that I showed you earlier, as well as neurons dying, which they do in Alzheimer's disease, those are the things that are leading to that interferon response, that elevated level of interferon that we see in Alzheimer's disease patients. And what my work shows is that that interferon might act back on the Alzheimer's disease pathology to make it worse. What's exciting is that we can reverse this effect using a drug that's already approved and is in clinical trial for Alzheimer's disease today. So I would like to thank you for listening. My name is Sophie, and thank you to my supervisor, Dr. William McEwen, for Wolfson Research Event for letting me present today, and to Alzheimer's Society who fund me today. Thank you.
Thank you, Sophie. Any question?
Thank you. So there's no suggestion that viral infection may be a common sort of initiator or enhancer of Alzheimer's, is there?
There is.
There is?
Yes, there actually is. So hospitalization after infection increases the risk of dementia. So if you have been hospitalized for a viral infection, that increases your risk of Alzheimer's disease.
But it's not the hospitalised. I'd always thought it's taking people who are confused into hospital, making it worse. No, you think it might be related to this?
No, I think there is a long-scale study, longitudinal study.
Okay, that's right. And is there any suggestion that people with rheumatoid arthritis who are being treated like this are less susceptible?
That is what I've wondered as well.
To developing Alzheimer's?
I don't know if I've looked for that data and I can't find it. So I think because the cohorts are so small, but it's possible, and I would really like to keep my eyes peeled to see if that's the case.
Okay.
Yeah.
And then maybe put the drug in the water for people my age. Thank you.
Thank you. This is probably a tricky question, but how do you think the interferon is interacting with the tau aggregates? How do you think that's increasing the tau?
Really good question. This is what I'm trying to work out in my final year. So I'm trying to see if it's... So those cells in a dish, that's a really quite nice model because I can take out different cell types and I can see if those are the ones responsible. So if I remove the immune cells from those cells in a dish, do you still get that effect? And therefore, is the interferon acting through the immune cells to have that effect on the tau aggregation? So I'm trying lots of different things, removing different cell types, trying to look at things that predispose tau to being more aggregation prone. So when you modify tau with a phosphate, it becomes more aggregation prone. Does that interferon make tau more phosphorylated? Does it increase the likelihood of tau aggregating itself? Maybe it's just internal. So yeah, this is all things I'm trying to work out. If you have any ideas, we'd love to hear them. Thank you.
Thank you, Sophie.
Thank you.
So the last presentation of this session will be delivered by Charlotte Clarke and is about the impact of privatization on children in care.
Hi everyone. So a little bit different from the science presentations that we've had so far, but I wanted to present this research, so a little bit about myself. I'm a second-year history undergraduate here at Wolfson, but the reason why I chose to do this rather than a history research piece is because it's not very academically researched. Children in care just aren't. So there's also a personal motivation. Before coming to Cambridge, I worked with foster youth, and I also grew up in the system. I guess it's a privilege we're not really used to at Cambridge to say I grew up in care, but I do see it as such because it gives me a unique perspective on a lot of things. So I want to just touch on terminology. So a child in care is someone who has been cared for by the local authority, so a council or a district. And a foster child refers to a child raised by someone other than their biological or adoptive parent. This includes kinship care, so like an auntie, an uncle, a grandmother. And next, I'm just going to give an introduction and an overview, a little bit of history, as I said. I'd be a traitor to my own discipline if I didn't. So in 2006, the government produced a green paper called Care Matters, Transforming the Lives of Children and Young People in Care. From this green paper, independent social work practices were introduced, allowing local authorities to contract out social work services for children in care and leaving care. Social work practices could include anything from social enterprise such as professional partnership or voluntary sector organisation, or private sector firms of various types, from shareholder-owned companies to small owner-operated businesses. This was seen at the time as the start of positioning for privatisation statutory social work services for children, and it has been commented that it crossed political lines often, and a former Blair advisor headed a government panel propagating mutuals viewed by Tories as merely a precursor to privatisation. This change in regulation effectively opened up children's social work services to the market. You could bid on anything, from court orders to where the child was being placed when they were removed from home. The introduction of a central government innovation fund for children's social services, with its policies and priorities, was determined by a programme investment board of 3 members from the investment banking private sector, plus the chief social worker for children and a former president of the Association of Directors of Social Services. The latter two both had been supportive of opening up more children's social work services to non-statutory sectors due to the cuts that were being put into the social sector and the overburden of children going into care due to inadequate home lives. In September of 2014, a Department of Education seminar took place. This seminar focused on how to create a market in children's social work services, as well as child protection. 3 months later, in December 2014, a workshop organised by the Department of Education, I should clarify that social services falls under the Department of Education as it relates to children as well. So this workshop in December of 2014 was in order to recruit new improvement advisors for children's services. It was attended, along with others, by G4S, a company primarily dealing in providing security to prisons. This will be extremely important later on. And others which also have a strong track record of gaining government contracts and not delivering on them, or with little to no recognisable experience or expertise in children's social work and child protection. Through statistics, case studies and government reports, it is clear to see that privatisation in its current format is unsuitable due to the unfavourable outcomes for children in care, but that is not to say that it doesn't have its place within the child care sector. It's time to start asking service providers in all areas when it concerns society's vulnerable children, is this good enough? Would you be happy for your children to be in some of these placements, or even to be treated like this? I also argue that there are many issues with privatisation when it comes to children in care. This is despite its apparent need, as previously said. Privatisation nevertheless prioritises profit over humanity and exploits youth trauma by creating a monopoly. The line of accountability and responsibility for what had been publicly provided services has become elongated, complicated and confused between contractors and contractees. The extension of choice is restricted when a small number of ever-expanding big outsourcing conglomerates come to corner the private sector, contracting out markets. The extension of, I've already said that, employing fewer staff in order to increase profits greatly impacts the children because they are not getting the adequate levels of support they need from professionals who are trained and specialised in order to recover from the complex trauma that is associated with being placed into care. By using private protection services like G4S, as previously mentioned, and other companies like Serco, with heavy links to the prison system, with a proven track record of overcharging the governments for services they are not even providing, it demonstrates a lack of regard for the needs of children over who bids for the highest contract, who bids the highest for the highest contract. So this next section takes statistics and explores what they can tell us about the impact of privatisation and children in care. So let's go to the numbers. 65% of children's residential homes are operated by the public sector, and 2 out of 3 of the biggest foster care placement providers in the UK are run by private equity firms. 28% of these privately owned children's homes in the UK fall below good Ofsted ratings, while 63 of the children's homes are classed as inadequate. There were over 11,000 more children in care in 2019 than there was in 2011. 73% of those additional children in care were cared for by private organisations. Here we see the numbers of looked after children from 2011 to 2019, organised by the type of provider. The ones important to this presentation are columns 2 and 4. As you can see, there was no increase in the number of children looked after by the local authority or the public. However, there was a 42.5% increase in the amount of children in care placed with private companies. Now, I'm going to talk about some demographics in the care system, and this will relate to how institutions often cross over and privatisation impacts many institutions. So, on the board, I've abbreviated to CLA, which means children looked after, because if you refer to a child as lack, it often insinuates that they might be lacking something. But we know that's not true. There is a so, as we can see, there is discrepancies with, I'm not a statistician, so bear with me. We can see that there are discrepancies between the type of ethnicity in populations that we all exist in, and how that often differs for black and mixed children in care, how they're overrepresented. And I'm sure you're all aware that black and mixed people are also overrepresented in the prison system. And one of the institutions that the prison system overlaps with most, and also, in my opinion, the most unregrettably, is the foster care system. Statistically speaking, close to 25% of the adult prison population have been in care. Nearly 50% of under 21-year-olds in contact with the criminal justice system, such as police, custody, courts, and probation, have also been in care. I asked you earlier to remember G4S. This is where they come in. G4S is a private security company, and they're also one of the biggest private companies with the prison systems and the care system. I'll leave you to make your own conclusions there. Is it a conflict of interest, or is it merely coincidence? Well, I'll tell you what I think. So, I wish to tie up these statistics with some analysis. First, I do not believe that it is a coincidence that children in care are overrepresented in prison. I believe this is because of a lack of adequate resources to rehabilitate these children from the trauma that they experience from being removed from their families. Furthermore, I do not think that it's a correlation that children from black and mixed backgrounds are overrepresented in both the care system and prison. These are both institutions which were founded on racist foundations. And now that privatisation has seen profits being turned in both, we see a further exploitation of people in society that are considered vulnerable and underprivileged. There are many concepts, ideas, and avenues that I would love to explore in this presentation. However, I simply don't have the time. But nonetheless, I'm looking forward to seeing where this develops in the future. And now, any questions?
Thank you, Charlotte. Is there any question?
Hello, thank you for the talk. I'm interested, how does the state of privatisation in the UK compare against the US and Europe as well?
So the US has an entirely different foster care system than we do, because they there's this piece of legislation called the United Nations Convention on the Rights of the Child. And every country in the world, it's the most ratified piece of legislation, except for the US. So they are completely unregulated. There's not as many statistics because it's kind of just, you do, in each state, do what that state's doing. But there's more profit in the American foster care system because it is much more unregulated than ours. And then you've got countries like Norway which just don't allow it at all, like the Scandinavian countries. So, yeah, hope that.
Yeah, so is it fair to say more privatization expected in the US?
Oh, completely, yes. Which, considering the healthcare system, is not surprising.
No, I would have expected it.
Yeah.
Thank you so much for your talk. I actually work in local government, so this was of particular interest to me. As you know, in local government, a lot of services are privatised for good or for bad. But I'm just wondering what are your solutions? Because as you know, children's social services and adult social care take up the vast majority of local authority budgets, and they're already struggling with the recruitment and retaining of staff. So one could argue that is one of the reasons why they look to private providers. So what would you suggest as an alternative? Thank you.
I don't think that privatisation is this all evil sort of entity. I think it has its value. I think where the problems come is when these companies are exploiting already traumatised children to gain a profit and not providing any service that reflects the price that they're charging. In some instances, they charge double to triple what the local government would charge for a placement. So I think some more regulations in terms of what these private companies can charge the government for these placements, and also a bit of accountability on the services that they are providing, because local authority government residential homes and foster carers have a lot more regulations than private companies do. So I think that might be a good first step.
Thank you very much for your talk. I think I do want to pick up on the question to ponder at the end, does G4S have a conflict of interest? Now, the way I look at that, now maybe I'm being a bit uncharitable here or a bit narrow-minded, is that for them to have a conflict of interest, they would need to essentially be purposefully neglecting children in care in order to make them more likely to go to prison. Now, that is an absolutely extraordinary hypothesis and assumes an extraordinary, almost inhuman level of malice on the part of the people involved. Now, I'm wondering, do I have this hypothesis right? And if so, or if not, how would we gather what I would say, extraordinary evidence we would need to prove a hypothesis like that?
So, in parts, yes, I do think that they are purposefully doing it. There's no reason for the statistic to be that high for the number of children in care to be in prison. And I think they are profiting in it in some way. It's almost like a conveyor belt. And as mental health services become more and more privatised, I think that's also another conflict of interest, is if you're not providing solutions at the core in this person's childhood, then they're going to go on and, not really know how to navigate life, and that will have negative influences. But I wouldn't know exactly how you can prove that without going up to these private company leaders and being like, do you hate children? Because the motivation will always be concealed in these matters, I believe. So, but as I said at the beginning, it's also quite a new kind of academic field for investigation. So, sorry.
Last question.
Hi, Charlotte. Speaking as somebody who spent most of his life as a head teacher, often in very, very deprived areas, I think that it would be interesting to investigate children in care, the prison system, and that element in the middle that relates to my life, and that is schools. Because I know that in my experience there were unprincipled head teachers who would refuse children to their school or would exclude them from their school. So when Ofsted, the inspection regime, came along, they would get a better report, or they would say to a particular child, and this is shockingly unprincipled, would you please stay at home for this week because we've got the inspectors in. Now for myself, as I say, a lot of my career I worked in very deprived areas. I refused ever to permanently exclude any child because my view was, if you do that, you will have a system where that child is excluded from one school, then another school, then another school, then another school, then they end up in prison. So I would just like to throw in to your investigation that element of schools and education, and suggest that perhaps the education system, the inspection system, should look at more deeply how many children are excluded from that school and build that into their reports.
So just as a personal anecdote and to close the whole thing, I was actually permanently excluded and now here I am. So it's not that children in care don't lack promise, it's that they're not given the environment to flourish, I think. But yeah, thank you everyone.
Thank you, Charlotte. So this is the end of this session. Now it's time to lunch. So please go to the lobby and enjoy the sandwiches there, and we will come back